Class, we're in the end game now. All this while we've been looking at electric fields, how to play with them, what are the forces involved, and all kinds of stuff. But now we're going to learn the final bit on how you control electricity. You will have the power to control electricity, or I should say the knowledge to do that. What are we looking at again? You may have forgotten already. We're looking at moving charge entering the electric field. Before this, we already looked at some charge that's starting to move and accelerate and decelerate. But now, we're going to see another way where a charge can enter electric field. So previously, when we see electric fields like this, if you have, say, a positive charge, let's say here, going inside a field this way, what would happen to this charge? Would it slow down? Would it speed up? Here is what we call the high potential, or the positive side. Then down there, we call it the low potential, or oftentimes the negative plate. So the moment this charge enters this electric field, it will start to accelerate once it reaches here. Why? Because you have a force acting on it in the same direction as the electric field. And we talked about so many times. So it's going to experience an acceleration, get faster. So how would you draw the path of this electron? Well, same thing, no. You just draw, you'll just keep going faster and faster, and then if you exceed it, then back to normal. No acceleration. Once it exit lah. So, at first no acceleration, you start at a constant speed, you get inside the field, suddenly you speed up. And then once you exit the electric field, you have a velocity, exit velocity, and that's it. So that's what happens to a positive charge. If you have a negative charge going in, starting off with some initial velocity, it's just going to travel at the same velocity until it enters the electric field. Like that. Once it's inside already, it's going to experience some kind of force. What is that force? Remember, charge, it's going to experience a force in the opposite direction to the electric field line. So Fe will be backwards. So what's going to happen to the velocity? We talked about in the previous example, it's still going to go forward, but it's decelerating, getting slower and slower until it will stop. And then probably start going back up. Just like that. Boing. Kind of thing. Kind of like dropping a tennis ball inside water. Okay, so it's decelerating. And we'll write that here. Decelerating. And that's getting slower and slower. Gets slower. And we know for sure there will be at some point where the final velocity is 0. Stop already. Then it might go back up. Because the force is still acting on it. So that's the difference between a positive charge and a negative charge entering an electric field. Now notice how the angle where they come in is parallel to the electric field. Just up and down, up and down, up and down. That's what we've been looking at. Up and down, parallel to the electric field. What about if they start curving? Is there a way they enter electric field, then they'll start curving the path? Think about it. Now they're just moving parallel to the electric field. Left, right, up, down, up, down, up, down. Remember how I mentioned a sneak peek? The electric fields are like gravitational fields. Where have we seen curved paths in gravitational field? You throw something, it curves. It's not going in a straight line. We have looked at projectile motion, don't forget. If you take any object and you throw it, if you throw it up, it'll come back down. If you drop it, it'll go down. But if you throw it sideways, it actually go like that and then kind of down. Kind of like badminton. When you hit a badminton or throw a basketball, it goes and it curves and then it drops down. That's projectile motion. We see similar things happen here. For example, this is what we're going to learn today. How to just add on a little bit of knowledge here. If you have a positive charge coming in, ding, 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 ding. Same velocity throughout this, not 0 lah. Some velocity is coming in. No acceleration, it's just the same. Then as it enters the field, it's going to experience a force. Where is that force going to act on it? Still downwards. Look at the picture on the left side. It's still downwards. So once you get in here, you will still experience a force downwards, like that. So is it going to straight away turn left and then go down? No, it's not going to do that. It's still going to have a horizontal velocity. So maybe a better way I should say is, this thing enters with a horizontal velocity, which is also the initial velocity. This is like projectile motion already a bit. So it's going to go still to the left, but a little bit down, something like that. Down, point. Then once it exits already, it'll just go straight. Straight line. Wow, so many lines. So it's going to curve. Because everywhere it is inside the field, it is experiencing an electric force pulling it down. 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 And no more electric force outside. So this electric force is going to cause it to have a vertical acceleration, AY. Is there a horizontal acceleration? No. Still, AX is 0. So throughout the whole journey, it will have the same horizontal velocity but an increasing vertical velocity, just like projectiles that we looked at. Okay, the horizontal velocity, same, horizontal velocity is the same, horizontal velocity is the same, but the velocity downwards is increasing. That's why it's curving. Okay, if you're ever confused, like, why is it curving? Remember, if this is a plate, here is positive, here negative. Your particle enter, but it wants to go to negative plate, so it will just slowly turn and then go until the negative plate. So same story, if you have a negative charge, then you come in with some constant velocity, which is the horizontal velocity. Okay, at first there is no vertical velocity. Uy is 0. Uy is 0 because it's moving horizontal, no vertical. Once it enters the field, zoom, 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 zoom. Where do you think it's going to go? Curve down or curve up? Take a guess. Well, first things first, the force acting on this is perpendicular to the motion, right angle, you could say it. So it's going to experience a force upwards. And therefore, it will start to curve up. So, something like that. And that's because everywhere, every minute it's in there, it's going to experience a force pulling it up. Force pulling it up. So it has some vertical acceleration upwards this time. But the horizontal velocity is still the same. So let me write down the facts. Horizontal, or maybe I should say the horizontal velocity, which is perpendicular to the electric field lines, is the same. This is a fact, which is the same in projectiles and also the same in moving charges entering fields as well. Okay, so just remember, all this while we're looking at those on the left side there, it's just up and down, you're moving parallel to the field. But now if you move perpendicular to the field, like that, then it'll start to curve, either up or down because the force is acting perpendicular to it. Let's look at some example past years that talk about this. This one's on page 13. Page 13. Whoa, a diagram thing. Which path shows a possible movement for an electron in the electric field? Oh, electrons are rebels, remember? They oppose everything. Now pause this video, take a quick guess or a smart educated guess on how you can think of where this electron will move. Think very carefully about the facts and then choose one of the choices. Pause the video, take your time if you need more time. Okay, so path of electron. First thing you want to know is, where is the force acting on this electron once it enters the field? Normally, if it's positive, we say point in the same direction as the electric field. But this is the electron. It's a rebel. So, we gotta do something else. So the moment this electron comes in here, it's going to experience a force upwards. Electric force. Oh. So it's going to start going upwards. It's going to get a vertical velocity that's bigger and bigger and bigger and bigger. So now we're left with choice A and B. Which one to choose? Choice A is a little curve. Choice B is a straight line all the way up. Hmm. Well, there's acceleration, and when you are experiencing a force, it's going to curve, just like projectiles. So you want to choose A and not B, because B is just straight line. So make sure, firstly, you know which direction your force is pointing. Is it up or down? And then you think of, oh, it's going to curve because it like to go to the positive plate. Okay, arrows come out of positive plate. So these are all positive, 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 negative, negative, negative. So the negative electron will want to go positive. So it'll curve over there and then park there. Okay? Just like how maybe you're walking on the side on the road, suddenly you see something attractive. Ooh, I want to go there. Then your body will curve there because you want to go there and see. All right. So that's the first intro one. Let's look at something a little more tricky. Same thing about diagrams. This question is on page 10 on a dipole. Here you have a molecule behaving like a dipole. Dipole means there's a negative, positive, marry together already, so-called negative, positive. They fall in love, they come together, they marry. Okay, sure. Page 10. Now this one, I want you to try it out also. Don't just like, oh, I will want to watch Miss Do. I just watch only, I understand already. No, try it out. Then you will see if you get it wrong. If you're wrong, then you know you don't know. Hint. Label the forces on the thing. Just draw on the picture up there and then just, draw pictures. Okay, so you have a molecule behaving like a dipole. Dipole means got two poles, a negative, a positive. Two equal point charges. So you can think of it as one charge here, one charge there. Opposite sign, fixed distance. Okay. The molecule moves with a constant horizontal velocity going into a vertical uniform electric field. Once it comes inside here, what's going to happen? They enter at the same time. So which row describe the velocity, horizontal and vertical component? Well, if I scroll down there, they'll say, oh, constant, increase, zero. How do we know what the component of velocity will change to be? First things, like I mentioned, draw the forces. I'm going to shrink this pen a bit so we can see. There's a negative and there's a positive charge stuck together. First things first, the negative charge is going to experience a force where? Against the electric field line. So this negative charge, this part here, will experience a force upwards, which is QE, F equals to QE. Then the negative fella down there, the other half, will experience, whoa, this is huge green color. This one, let's change it smaller, will experience another force, but downwards in a different direction. Wow, like that how? Where would it go? Would it go up or would it go down or would it not go anywhere? It's like two people, a couple together. One say, I want to go McDonald's. The other one say, I want to go KFC. So in the event where you go, you cannot decide. One force pull there, one force pull there. So what's going to happen is, this FE is the same magnitude. So there's going to be no vertical component. No vertical velocity. Why? Because no net force vertically. Because FE and FE cancel out, one up, one down, so there's no net force. Means there will be no vertical acceleration. Otherwise, what we call as AY. So vertically, nothing's going to change. Horizontally, is anything going to change to this velocity here? Is there any horizontal forces here? No, there's no horizontal forces. So it's just going to keep going at the same velocity, just cruising along. The negative and the positive. So I should mention, there is no horizontal force, horizontal net force I should say, but no horizontal force. So there's no horizontal acceleration, left to right, nothing. So it'll just keep at the same velocity as before. It enter with the same velocity, it exit with the same V. No change. With that in mind, now we can look at the answer and see, oh, which one is it actually? So we already say vertically, There should be no vertical velocity at all. So that means 0. So this 2 is out. This is correct. And horizontally, it's not going to increase because there's no acceleration, there's no horizontal forces. There's only a force up, force down, the electric force. So that means it'll be constant all throughout the whole journey. Okay, this one is like the normal particles but 2 joined together, so you can see like, oh, you need to be able to think. Don't memorize. Try to understand the principles behind it. Because this, then this. Because this, then this. Okay, that's called reasoning. So we're going to go to a summary now in the handout so we can see what are the factors that affect how a particle curves. Okay, let's take a look at the section in the handout. So let's say I have this electric field that I created. Pardon my drawing, a bit crooked today. Let's say I have this electric field. I connected one side to positive terminal of the battery, the other side to a negative or ground, and I send a positive charge into this thing. What will be the path that it takes? Well, we have established earlier that it will be straight at first. Once it enters the electric field, it will start to curve. So maybe curve like that lah. Touch there. That's what we call the path of the electron. So how do I change this path? What if I want the path to go maybe further a bit? How do I get that? What do I change about this charge or this system? Now, how fast or how quickly they touch the plate or how quickly they turn left depends on their vertical acceleration, AY. If they're accelerating upwards very big, then they very quickly they turn left already, like that. Wow, that's a bit too fast. But you get what I mean. It depends on acceleration. So previously, did we look at acceleration? We did. This was from the previous video. We say, oh, a charge experiences a force. So that's related to the acceleration. So you need to know how to derive this equation, by the way. A equals to QE over M. Good to review that a bit if you already forgot from the last video. How do we get QE over M? That's the electric force related to Newton's second law. So we can apply the same thing here. If you want to see what affects these paths, let's look at acceleration, or maybe I may use different color here. Jam already my pen. Acceleration is related to QE over M, like what we talked about earlier, right? There, I did some magic to make it blue color. So acceleration related to QE over M, as I mentioned. But what if we focus on the vertical acceleration? Because we want to see how fast it go up, accelerate up. How fast is the vertical velocity change? So this is really vertical acceleration equals to QE over M. Horizontal, no acceleration. AX is 0. Because all the forces are only pointing up and pointing down. The up, down, and left, right don't affect. Vertical is vertical by itself. Horizontal is horizontal by itself. They don't affect each other. Because vectors, Okay, so we have AY equals Q over M. Means this AY tells us how quickly the particle will deflect. Deflect means bend up or bend down. So the bigger A means it go up faster. So let's see. Q is a factor, E is a factor, M. Let's focus on Q and M in this case. So Q is the charge. If the charge increases, do you think A will increase or decrease? If suddenly the charged particle is very, very big charge, do you think it will go up quickly or go up very slowly and then kind of take longer time to bend there? Well, if you think of it, charge, stronger charge means stronger attraction. So A will increase. It will go up very quickly because it really, really wants to go to the opposite side. Or if you look at it mathematically, if Q increase, A also have to increase to balance out the equation. So yes, the stronger the charge, the quicker it will bend. So let me draw another line here. Point. So the first thing is, if you have a charge that is very big, it will bend very fast. Then smaller charge take longer to bend. Even smaller charge take even longer to bend because it's small charge, no attraction. Just like, okay lah, so what? I will go there eventually. That's what the charge does. Then, let's rewrite this again. What if I change the mass of this particle? For example, let's say I make the mass smaller and smaller, decrease mass, lighter and lighter. Or I should say, what if I increase the mass? How does mass affect how quickly it will turn left? Think of it this way. If you are very, very heavy, lots of mass, it's harder for you to suddenly change direction and turn left. So you take longer time. You have to like, oh, okay, turn left. Then you finally turn left. Or you could think of it this way. A is inversely proportional to 1 over m. So if m increase, A must decrease. Which means the bigger your mass, the slower it will take you to turn left. So if you are very, very heavy, a very large mass, like this m, wow, you will take very long time. There will be this one here. You will take that path. Path number 3. If you're a bit lighter, you won't need so long to turn left. You accelerate upwards pretty quickly. By the way, oops, wrong sign. You know why? How is force and mass related? I need to remember a bit. How is force and mass related? So, yes, the lighter you are, the quicker you will turn left. And that's what it's telling us. So, lighter particles deflect quicker. Very quickly, they turn left and then accelerate because their vertical acceleration is quite high. And then, of course, the conclusion from the other one is larger charge magnitude will deflect quicker. And that's pretty much the summary of this picture here. How to think of things deflecting, and it's all based on this equation that we looked at. Charge and Newton's second law. Okay? So take some time to digest this thing. Now the last question before I close up or close the ending of this video is something to do with these factors. It's on page 17. If you can jump over there very quickly. Here we are, page 17, MJ18 P13 Q28. This one I consider you could consider it a challenge question if it's the first time you're doing it. But once you get the hang of it, then it will seem, oh, I've seen this before. No sweat, no sweat. So here, you have a particle, mass and Q entering a field with speed. Oh, it's bending. Zzz. Deflection, the proper word. Initially, it's traveling at right angles to the electric field. So that's what it means lah. Your electric field line is going to be like that. And it's traveling right angles. Ooh, let's change that. Then, when it moves through the field, this gray part, the particle is deflected. Deflected means it bends like that. A second particle comes in. This time, it's a little bit heavier. Mass 2m. Charge is the same, right? Q and Q. Okay, charge is the same. And the same speed also. Now enter. What is the distance where it is deflected? So it should have a new deflection. Here the old deflection is D. What is the new deflection? Oh, this one also must pause video and try out by yourself first. Don't give up if you're stuck. Take a break, go drink some Milo, come back, and then try to see what are some ways I can think of this relationship. Hint, hint, it has to do with equations and what factors affect what. So yes, pause, take your time, and let's go through this together. Yup, let's see how to do this. Okay, so previously we said, oh, A is QE over M. But how can we even use that here? This has distance inside or deflection. This is where, hint, you will need to use some ideas from kinematics. Chapter 3, Stuva equations will need to be used here to help us out a little bit. So we're trying to find, oh man, distance of deflection, so this D. You can also think of it as vertical displacement, also what we call S of X. Vertical is X, sorry, blurs, yeah. S of Y, that is the one. Vertical displacement, SY is our D. We need to create an equation that relates SY to the mass which is changing. But how do you relate displacement with mass? Let's throw out all the equations we know, just list everything out. Okay, so we know A is QE over M. How do we proceed from there? Do we know any Stuva equation that has S in it? I think V square, U square. Oh, well, we don't know U. Let's try this one. S equals to UT plus half AT square. But I want this for my vertical component. So S of Y, U of Y, A of Y. All for vertical only. Then we can plug in what we know about this thing. S of Y is what we call D. Okay, so I'll just rename it as D. Is there an initial vertical velocity? This one. Is there an initial vertical velocity? There's a horizontal and there's a vertical. No, I don't think there's any. 0. Because it's fully horizontal, so cannot have. So this whole thing is gone, just 0. So all that's left is half AT square. Now what? I want to relate this D with mass M. Where do I get any other equation? Wait, on the left side, we wrote this just now. M. That's the thing we want to involve here. So I'm going to plug it in. Okay, so D equals to half QE over M T square. Wow, this is looking very strange. Is there a way I can simplify this equation? Yes. I only care about the relationship between D and M. So I'm going to zoom in on that. So I'll say D is proportional to, where is M? Here. So 1 over M. Oh, that's the inverse relationship. Okay, this proportional thing is how you determine what's the relationship of it. So now that it's 2 times heavier, what's going to be the new D? Here's a shortcut or a very easy way to think about it. You rewrite it first. Okay. Now you change the mass to 2m already, so 2m. If you want to balance this relationship, what do you have to add on the other side? 1 over 2 also. Okay, so we have to add 1 over 2. Okay, so that now it's 1 over 2d, 1 over 2m is balanced. That means it's going to be half of the original deflection. So the answer here will be d over 2. Means if you actually drew out the deflection, okay, it's going to be a little different than the original one. Because this fella is a bit heavier, so it's going to take longer to curve downwards. So something like this. Slowly take time to turn. And this is for the heavier particle of 2m. This is a particle of m, like what we did. Okay, so this is a very good tech skill to determine relationship between things. If you change this, what happened? If you change this, what's the factor of the other thing changing? If you change m, how is the deflection going to change? Okay, let me scroll a bit so you can see that. All right, so this is the main idea of how to think about deflections. Bring in your Stuva equation. Use all your electric field equations and put them all together. There is one more challenge question, but I'm not going to talk about it here because it's pretty long. It's actually a paper 2 question, but instead I'm going to say, go try it out by yourself first. I will upload a bonus video or do a discussion in class about this question. It's very fun. It's bringing together all the kinematic stuff and like stuff we looked at just now. All right? So with that in mind, you have really learned a lot about electric fields and how to control electricity. Remember I mentioned earlier, right? I said you have the power to control by the end of this video, you will know how to control electricity. Do you see the connection? Do you know how to control electricity yet or not? Let me give you some ideas before we close the video. Ta-da! This is called a Crooke's tube. Why is it called a Crooke's tube? Well, because the guy Crooke invented it. There are many other similar devices here. Now, what you are seeing here is not a lightsaber, although it could be a lightsaber if you turn it into one. But what's happening here is you actually have high voltage and you got particles inside there. Let's show you the particles. Charged particles like electrons or something like that. And they're all moving. You see them very small. They're moving up and down, flying to the right. So what's happening is you first have two plates. This one and this one. These two plates will accelerate the electron horizontally, left to right. So they will start moving to the right. These are all electrons, okay? And then what is these two plates for? These two plates will control whether your electrons go up or down. Now you can see it clearer if it's a beam. Okay, so remember, the first two plates here is going to make it accelerate to the right, go faster. Then these two plates will control it, make it go up and down. Let's show you the beam, okay, to see clearer. So, okay, we got this laser special thing. I'm going to change the voltage on these two plates now, and we will see how the beam can deflect. So if I change the top to a positive, ding, 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 ding. See what happened to the beam? You kind of just controlled the beam to go up. Basically, you're controlling electricity in the sense, I can think of it that way. Then if you change the top plate to become negative, ding, 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 then it deflects down. Because now there are different forces acting on all the particles which form up a beam. So we talk about beams, and this is one way where people control all these electrons to do amazing things. One of the ones that you all have seen before is the CRO. You guys remember what CRO is? It's from chapter 2. The CRO is the one where you see waves like these. Notice what they did here. Firstly, you have something that will create all the electrons, okay, on the far left there. Then you have one plate to make it go up, make it go left or right, and another plate to make it go up and down. Basically control both directions, X and Y. Then they will create all kinds of funny patterns like this. Zoom, 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 zoom. And these are the CRO patterns that you see on the screen or on your exam paper. So very cool things that people have been doing. They control the electricity to create patterns on the screen. You may have seen this before in IG, called the Cathode Ray Oscilloscope or Cathode Ray Tube. This is the technology. People using electric fields to control electron beams. But the most cool application of this is probably one that we are very familiar with but didn't really know how it worked. That is the TV. Maybe you've seen my tab up here. See this thing? Okay. I have a picture of the dinosaur. Not the actual dinosaur. Pause. Let me get it for you. I'll show you what I mean. Now this is what I call the dinosaur. Have you seen this thing before or not? Or are you too young to remember this? This was the old computer monitor before all the new technology and smartphones came out. It is very heavy. That's why I'm holding it at such an awkward angle like this. Okay? So this thing, the technology is a lot of electric fields going inside. In fact, very, very high voltage inside here. I don't simply open up. It's so big because it is an electron gun inside. Pew, 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 shooting electrons out, up and down, left and right. And how those electron beams scan this surface is the image that you see. Your house may have some of these computer screen or old TV, maybe you remember from last time. I would open this up, but I don't have my tools and I'm like, it's high voltage, maybe not. So I'm going to show you what is inside this computer monitor. Oh my goodness, thankfully I didn't drop it. Oh, I'm very scared. If dropped then, how? So here, let's take a look. Very quick one before we end. It's an old animation, but I like it because it very clearly explains what's going on. So here, let's take a look.
How does the monitor work? Signals from your computer's video card are loaded into 3 electron guns at the base of the monitor. There is one gun for each of 3 colors: red, blue, and green. These 3 colors, when mixed together, can create all the colors you see on your screen. Now, these guns don't shoot bullets. Instead, they shoot a powerful beam of electrons towards the face of the monitor. The beams pass through the deflection yoke. It uses magnetism to bend the electronic beams so they can sweep across the entire screen and create the picture we see.
I'm going to stop there because they go on to explain other stuff which we don't really need to know. But notice they say, oh, use magnetism to deflect. That's another way you can control electron beams. But FYI, oh man, we can control electricity and do great stuff now. Of course, now technology has evolved. You have smartphones which are really slim. They don't use electron guns anymore. There's also one more very interesting video, but I won't show it for the sake of time. I won't show the whole thing. It's by the slow-mo guys. The full video is down in the description below. But basically what they did is they took a video of the screen and they slow it down so you can actually see the scanning line by line. And that's what a lot of electrons are doing when they hit the screen. You see it line by line coming down. So very informative, very interesting. Go take a look if you are interested. But yeah, that's the bit about applications and how you can control electricity, electrons, charged particles. Lots of research do that. So go try out this challenge question that I have listed here. Try this. Brainstorm with your friends. Don't give in to look at the mark scheme so quickly. Got to build that resilience and problem solving. All right, so yep, this was all that I showed you. And so we're done with chapter 17. What a journey. This is our introduction to the electric world. We learn how to draw field lines, like, squares, things like that. And we know how to define what is the electric field strength, calculate E with either V over D or F over Q, two ways. And also, of course, force on charge is QE. And find work done, we related it to chapter 6. And lastly, the 17.3 A, B, and C. These last three videos talk about the different effects on charges inside the electric field. We talk about what if there's charge floating in equilibrium in the electric field? What does that mean? What if there's charge moving into an electric field? What does it do once it enters? All these kinds of stuff. So this chapter 17 will be fundamental for some other topics in A2. And moving forward, we will be going on to the world of electricity. Wow, the world of electricity. Well, pretty cool stuff. But make sure you know your basics. What are electrons, how to deal with them, and why they flow. So that was all for chapter 17. Go try out the challenge question, and I'll see you in the world of electricity.